thinking of this problem, 78 here, let z be a standard normal random variable, and let y be 2z squared minus 1. Find the density for y. One of you, I think it was Noah, used the fact that z squared is chi squared, which is fine. But I wasn't necessarily thinking that you'd have to do it that way. Z is standard normal. Remember, we talked about this. Z squared would be chi squared with 1 degree of freedom, to be more specific. But let's use the CDF method again. So y is 2z squared minus 1. Z is standard normal. Y is 2z squared minus 1. We want to ultimately find the PDF for y. We want to use the CDF method to find the PDF, because I think it promotes understanding, whereas the book's formula involving the derivative of the transformation is just a little bit more mysterious. It's like sometimes quicker, but more mysterious. CDF for y, capital F sub y of little y. We want to find first, and then we want to differentiate it to find the PDF. As I've said over and over again, this is always the probability that the random variable, the capital letter, is less than or equal to whatever the little letter is there. Okay. The capital letters are random variables, abstract ideas, you might say. To be technical about it, they're functions, but we just treat them as intuitive abstract ideas. Makes sense, intuitive abstract. I don't know if that makes sense to put those words together. And the way you do it is you want to relate it to the PDF of Z, or the CDF of Z. Z is standard normal. So this would be one of those situations where I'd want to use that capital phi notation, or I could at least, not that you have to. But we do technically need to be careful here because Z can take on positive or negative values as well. That's another trick here. Makes this a little trickier. Probability that Z squared is less than or equal to 1/2 y plus 1/2. Take the square root, but because Z can be positive or negative, when I take the square root, I really should think in terms of the absolute value of Z. Oops, square root symbol. There. The square root symbol on the right side of the inequality implicitly means positive square root, but Z itself could be positive or negative. And so I really want to say its absolute value is less than or equal to the square root on the right. Which means Z itself, this is good practice for real analysis if you haven't had real analysis yet, absolute value of a number is less than or equal to another number. That means the number itself is between the opposite of this number, square root of 1/2 y plus 1/2, and that number itself. The absolute value of A is less than or equal to B, where B is implicitly a positive number. That means A itself is between negative B and positive B. And this is really the difference of two CDF values. Capital phi of this minus capital phi of that. Or if you prefer, like I did when I derived the fact that Z squared was chi squared with 1 degree of freedom, you could use the symmetry of the normal curve. Symmetry. To say this is 2 times the probability that Z is less than or equal to the one on the right. And in terms of, well, I made a mistake there, sorry. 2 times the probability that Z is between 0 and that number. And in terms of the CDF of Z, the standard normal, that'll be capital phi of the square root minus capital phi of 0, but we know by standard normal distribution that that's 0.5. Since Z is standard normal, the CDF value at 0 would be a half, right? With half the probability under the standard normal curve is to the left of 0. It's symmetric around 0, the PDF. Bell-shaped curve centered at 0. And then distribute the 2 through it back through, and you can write this as 2 times capital phi. I'm going to write the square root now as a 1/2 power, because I'm going to differentiate. And then 2 times a half is 1. So this is a formula for the CDF of Y, which again is 2Z squared minus 1, in terms of the CDF of Z. And again, we only use this capital phi notation for the standard normal distribution. And you don't have to use it. You could call it F sub Z instead, capital F sub Z. But now we differentiate it to find the PDF of Y. So we need to use the chain rule. And we're going to get another derivative. The derivative of the inside is going to be 1/2 y plus 1/2 to the negative 1/2. Then we use the chain rule again and get another 1/2. One of those 2's can cancel. You can ultimately write this as 1/2, okay, 1/2 y plus 1/2 to the negative 1/2, which of course I could also put in the denominator as a square root. I'll write F sub Z of 1/2 y plus 1/2 to the 1/2, where F sub Z is the PDF of a standard normal, which I don't think has a standard notation, not like a lowercase p. But the PDF is something we can look up. The CDF, the capital phi, has no standard formula. A non-standard formula for capital phi involves ERF, right? The error function. Integral of the PDF of the standard normal involves ERF. It's just notation for the CDF. But the PDF does have a formula. That one. So I got to replace X. Well, I'm replacing mu with 0 and sigma with 1, which makes it simpler. I replace X with that square root. And I'm going to end up squaring it, so the square root's going to go away. There's also a square root of 2 pi down here. Sigma is 1. I'll go ahead and write it with EXP. EXP, negative 1/2. The square root's going to go away. You're going to have a 1/2 y plus 1/2 in here. You could also write that as y plus 1/2. What's the domain here? We haven't thought about the domain yet. What's that? Did I forget the 2? Oh yeah, I forgot that. Sorry. Yep. Okay. I forgot this. Yeah. Okay, put that in there. Sorry about that. Domain. Domain is important, as we're learning in this class, right? Piecewise functions, domains. You learn about it in pre-calculus. You wonder, why do I care about piecewise functions? Well, in case you take prob and stats or this class, that's why you care. And there's other applications too. You know, Z is standard normal. Values of Z, little z, could be any real number in theory. But values of Y can't, because they're values of Z squared times 2 minus 1. Can't get less than -1. Y is greater than -1. It's not a big deal if you put greater than or equal to, or just greater than, because it's a continuous random variable. This is for Y is greater than or equal to -1. Yeah, don't forget this part here. Is this a familiar PDF? Maybe you didn't look it up. I looked it up and I see it's actually almost familiar. Almost. It seems to be almost a chi-squared. With how many degrees of freedom? 1 degree of freedom, actually. Maybe that makes sense. Z squared was chi-squared with 1 degree of freedom. This is a linear transformation of Z squared. It's 2Z squared minus 1. Yeah, it makes sense. It should be related to the chi-squared with 1 degree of freedom. The 2 with the little gamma would be 1, so you'd have 2 to the 1/2. That's analogous to the square root of 2 there. The square root goes over the pi as well. The other 2 in the pi will match capital gamma of 1/2, I believe. Actually, I think capital gamma of 1/2 might be just square root of pi. So that extra 2 is not, maybe not clear where that comes from or where that goes. Capital gamma of 1/2 is just square root of pi. So the extra 2 here might be related to the fact that in here, we replace x not with y or y plus 1, but y plus 1 over 2. Maybe that's where the extra 2 down there comes from as well. And yeah, this part here, the x gets replaced by 1/2 y plus 1/2, and little gamma is 1. 1/2 minus 1 is -1/2. So it's kind of like a transformed chi-square with 1 degree of freedom. Not exactly chi-square, but a transformed chi-square. Let's do some simulation with this as well, just to re-emphasize some simulation ideas. So I could do something like this. I could do Z data. Random variate normal distribution 0, 1. Do 100 times, say. There we have 100 observed values of a standard normal. I'll suppress the output. And Y data, well, I need to define my transformation here. 2z squared minus 1, maybe I should call that h of z. 2z squared minus 1. Y data, to obtain that from Z data, I want to apply that function to all the Z data values. Map H over Z data. None of those numbers are less than -1, though many of them could be close to -1. We could make a histogram of the y data. Hopefully it looks like some sort of shifted chi-squared. It should be right skewed. It should go down toward -1 though. Well, maybe I don't have enough data to see that. Okay, you can see it goes negative here. And yeah, that's around -1 there. The origin's not in the usual place, this vertical axis. See if I can force it. There we go. Do it. Maybe we do 1,000 data points. Or how about 10,000? But I want to suppress the output so I don't have to see it. There we go. Chi-squared with 1 degree of freedom. What does its PDF look like? Does it have that kind of shape? So this one's not going down towards 0 near -1, right? It's a large tall bar there. If you plot the PDF, a chi-square distribution with 1 degree of freedom as a function of x, does it go up first and then down, or does it just go down kind of like just an exponential decay? 1 degree of freedom, it goes down like an exponential decay. If there's a higher number of degrees of freedom, like 10, it'll go up first, I think, yeah. Before going down. Even 2 degrees of freedom does that. Well, maybe 3 degrees of freedom does it. 1 degree of freedom doesn't. Very steep there. It doesn't have a vertical asymptote, but it's close to having a vertical asymptote. It does have a highest value. Okay. How about limit? Okay. Yeah, I'm pretty sure it has a highest value. Maybe I'm wrong there. Yeah, I think I probably am wrong there. Actually, probably does have a vertical asymptote is what I'm trying to say. Anyway, the histogram will not have a vertical asymptote. Histograms can't have vertical asymptotes, but it's decreasing and shifted to the left. And like intuitive sense that would happen. You think about a standard normal distribution, there's the PDF, standard normal. Simulated data values are going to cluster close to 0. Every once in a while, not. But they'll almost all be between -3 and 3. The transformation, think of this as a z-axis here. And think of this as a y-axis. The transformation y equals 2z squared minus 1. If you graph it, it's going to be a graph that looks like a parabola opening upward, about like this. That's not a PDF, not a CDF, it's a transformation. I'm trying to imagine transforming the data values on the z-axis horizontal to corresponding data values on the y-axis is what I'm trying to do. Points close to 0 for z will get mapped close to -1. Plug into the red function, that function, you'll get close to -1. That's why there's so many values close to -1. Points a little further away will get mapped to points a little further away from -1 if you're further away from 0 on the z-axis. Points really far away over here could get mapped to positive values of y. But that's going to happen less often. The data along the transform data along the vertical y-axis here is going to cluster close to -1. That's what we saw in the histogram. Although y was horizontal with the histogram. In this picture, it's vertical. this kind of picture can give intuition. The green graph is a PDF, the red graph is not a PDF. Red graph's a transformation. Imagining data being transformed from the horizontal axis to the vertical axis. I think it's pretty cool to think that way.